this session. So to get a pulse before getting started, right? I just want to know how many of you have worked with microservices. Yeah, great. How many of you have just heard microservices but not have worked? Okay, almost everyone has worked with microservices, which is great. Okay, how many of you have done distributed tracing or any observability uh, backends, frontends? Okay, nice. So my talk is going to be about distributed tracing, and we'll see the various challenges we face when running microservices in production and see how these challenges can be overcome by using distributed tracing and observability. Okay. A bit about myself. I work as a developer and DevOps engineer and equal experts. My background is primarily application development and infrastructure and DevOps. Primarily, I have worked with platform engineering teams. Yeah, I go by Arunvel Sriram in GitHub and LinkedIn. Yeah. So before entering the actual distributed tracing, right, I would like to introduce the simple application which I developed to demonstrate the distributed tracing. It's called Gringotts Bank, which is a bank for wizards from the Harry Potter movie. So this bank's application is following the microservices architecture. If you see, right, it has a bunch of services. We have a front end service which kind of acts like a orchestrator that talks to other microservices. Then we have the customer service backed by a Postgres database. We have a payment service backed by Postgres database, and we have a recommendation service backed by Redis. Actually, there is no reason to use Redis and all here. Just to demonstrate a complex microservices system, I have just used it. Okay. Yeah. So the API that we are interested in in the Gringotts Bank application is get recommendations API. Okay. So get recommendations is going to return uh, the offer recommendations for a given customer. Okay. Uh, so front end service, when we invoke the recommendations API of the front end service, it's going to make a call to the customer service internally and get the customer details to verify the customer and validate the customer. Once it gets the customer details, the front end service is going to call the recommendations, it asks the recommendation service to provide recommendations for that customer. Now, recommendation service is where all the computation is going to happen based on the customer details and the transactions of the customer. It's going to generate some offers. So it's going to get the customer details from customer service, and it's going to get the transactions from payment service. Once it gets both these things, it's going to execute some rules internally, and it's going to come up with some offers. The rules can be something like if the age of the customer is let's say greater than 65, it will come up with some senior citizen FD and RD offer. Or let's say if the customer is having more than 50 UPI transactions in a month, it's going to suggest a UPI credit card offer. Some random rules which I have coded inside to get some output. Okay. Fairly simple application with four microservices. Okay. So when putting this application in production, right, definitely we'll face some challenges given the nature of the distributed components inside the system, right? So if it is a one monolith, it's going to be a simple application. When issue comes, you just go and check the logs of that particular app. There is going to be only one connection. The app is there and the database there. But here we have four services. Each has their own databases. There are a bunch of HTTP calls happening. Then systems are going to talk to database. It may talk to some third-party APIs. All these things happen, right? So first one is the end-to-end visibility. So it will be good if we can say that, okay, if a request is coming, then this is what is happening within my system. If we can see it somehow, right, it will be great. Then identifying failure points. So there are a lot of things happening within the system and a lot of interactions are happening. So any failure can happen at any time. For example, when getting the recommendations, if there is a failure, we won't know where exactly it's failing. Like there are 4 services. We need to go and check the logs of all the services, and we need to identify where exactly it's failing to nail down to a particular service, then particular section of the code inside that service, all these things, right? So that is another pain point. And the last one is performance issues. Lot of interactions. Obviously, there will be some performance issues. The database can take more stress. If it takes stress, it's going to affect the driver which is making query to the database, which is going to affect the previous service. Like that, it can cascade as well. So that visibility, if we have to improve the performance, first we need to identify where exactly the latency is compromised. To identify that itself is a challenge. Once we identify, yeah, anyone can go and fix it. So this challenges, yeah, these are some of the challenges, but obviously there'll be many more challenges as well. So these challenges, right, we'll run the application and simulate and see first, and then we'll see how tracing or observability will help us solve these things. Okay, I'll switch to the browser. So this is the Gringotts Bank application. So it is I have written it using Golang. How many of you have worked with Golang? Okay, yeah, it's going to be simple only. Like you can relate it with any languages. Like it's primarily going to look like C. Okay, yeah. I hope it's visible to the back. So as I said, every service has their own DB, right? So to set up to run the dependencies, that is a DB and Redis, all those things, I have used Docker Compose. And along with that, I'm running some components for tracing, which we'll cover later. So first I'll start the dependencies. Yeah. So the databases are running now. Then we'll start all the applications together. I have this make target called make run, which is going to build all the services and then start all the servers using the GNU parallel command. It's going to start everything parallelly. So as you can see, we have front end running in 8080, recommendation, customer, payment, all these things are running. So we are using a web framework called Fiber from Golang. You can think of it as like in Java, we have Spring Boot, right? Similar to that, in Golang, there are multiple web frameworks. I'm using just Fiber. It's called Fiber. So it has started Fiber server for each of the application. Okay. So now I'll access the UI. It's running in 8080. Yeah. Okay. So let's get the offer. I'll also open the network console to, yeah. So we'll try to get the offers of the customer with ID 1. So we can see that the customer name is Harry and he has these many offers. Okay. Now we'll look at how to get that end-to-end visibility. So I have a tool called Ager running, which is going to show all the distributed, all the traces. Okay. Yeah. So I'm going to query using the customer ID. Yeah. So we can see that there is one request for the recommendations endpoint for this customer with ID 1. So if we look at this trace, right? It's called a trace. We can see that what is happening within the system. Like the request came to the exact flow that we saw in the PPT, right? It's completely visible. Like the request came to the application server, the application server of front end service. Then from the front end service, it front end service has made a HTTP call, initiated a HTTP call to customer service. Then customer service, to get the details of the customer, it has made a query to the database. So like this, the entire flow, if you see, the entire flow is visible till the recommendation. So if we expand one of this uh, section, right, we have few more details. This is the recommendations API handler. So if you see, the request came into the system. So it has all the request related information. What is the HTTP method? What is the HTTP path? All those things. Then interesting thing is it will have the response related details also. So once the request is completed, it will put back the response related things into that particular section. So we can clearly see that, okay, a request comes and this is what happened inside the system. And we have few more information related to the application or the infra in which the application is running itself. For example, in my case, I am directly running in the my Mac machine. So it has put the host name. If your application is having a number of instances running across many different VMs, it's going to put the host name of the VM. Or if you're using container, you can even put the container related container metadata into this. So we know the request, where exactly this particular request, in which particular machine it went, which container it went, all those things, we can see it in one place. Then we have logs. Logs is another interesting thing. It is contextualized. So the request came inside front-end service. Whatever logs that was put by the handler alone will appear in this section, which means we know that, okay, this operation, this small operation happened, and inside that, what logs, what events got emitted. So it's like uh, every step we can just go and see like what is happening. Even next call, if you see the HTTP request is made by the HTTP client, then we'll directly go to the database. It reaches reach the customer, and customer is making a database query. Even that is tracked here. So this is a Postgres. GoArm is a Postgres library for in Golang. So if you see, it made a select statement in Postgres, and what is the how many rows are affected. All this information, what is the client name, what is the client library that is providing this information, all this information is going to provide. So we know that how much. Even another important thing is each step took how much time. Totally that duration of the request is 39 milliseconds, and each step, if you see, this has taken 14 milliseconds. This has taken okay, it's not visible here somehow, right? One second. Yeah, it has taken the entire request took 39 milliseconds, and this HTTP request to customer service has taken 14 milliseconds. Like that, we can see every step how much time it took. So it is also easy to identify where exactly there is a bottleneck in performance. So what we'll do, we'll just go and simulate an error. We'll get the offers of the customer with ID 4, and we get an error saying failed to get recommendations. Now we have 4 services. Where is the error? So let's try to see by accessing customer with ID 4. Yeah. So if you see, there is one request to the customer with ID 4, and this itself shows that that request ended up in an error, and where in which services we have error. For example, we have error in the something in the front end is marked as error, something in the recommendation is marked as error. So let's expand and see. So the request came to front end and it ended up in an error. So inside that, if you look at the status, it would have marked this section as error, and the status code is 500. Then if we follow the series of calls, we see that it entered recommendation service and then it failed. Now we open recommendation service and understand what is happening. So we'll look at the logs. There are a bunch of logs. So here, if you see at line number in recommendation server line number 88, we are intentionally raising an error for customer with ID 4. So like this, we can nail down where exactly the issue is happening and then go to that point and then fix the issue. So it's going to reduce the turnaround time for any incidents as well. Let's say a customer is reporting an error to your customer support. It's not going to be like the customer support will send an email to someone, and then they go and send an email to other people, some team, then some manager or someone is going to find out who is responsible for it, and then the turnaround time is going to be 3-4 days. Here you have one tech support team who just knows that where exactly things are happening, and then they just tell that, hey, okay, this service is what failing and this is the issue, okay, fix it. So we provide a better, uh, better response time for the customer, and it will help us help them to gain more trust on our system, right? Yes, yes, sure. Mhm. 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 Yeah, so there is also a way. This is just a filter I have applied. We can look at all the traces as well. For example, we can do error equal to true and search as well. And this distributed tracing is one part of observability. There are also other parts like metrics and monitoring as well. So it's not that always we end up in the tracing first. Sometimes things can come through monitoring as well. We look at monitoring dashboard. There are a lot of 500 errors happening. Then we figure out which path is causing 500. Then we come to tracing and filter those paths and then understand the error as well. So one part of observability is distributed tracing. Other parts, we have logs, we have metrics, we have monitoring, all those things. So everything complement each other. Yeah, we'll look at one more customer for performance issue. We have the customer with ID 6. So this customer, right, if you see, it's going to take a lot of time. Yeah, it took, I think it took around 5 seconds to get a response. So now, if such issue comes, the customer will mostly they will we get they'll get frustrated and they'll call the customer support and tell that I face an issue, right? So finding where exactly is the issue, that is going to be the biggest problem with performance issues. So let's go and put this back and search 6. So if we look at the total duration of this request, it is 5 seconds. Now, if we open all the operations, we see that almost everything is in milliseconds. Just this one part, if you see this black color, right, this particular operation alone is being done from starting to end, which means there is some issue there. Something has happened there which is taking more time. So let's expand and see. So it took 5 seconds. We'll check the logs. So we see I have just introduced the delay there. So I have put a 5 second sleep there. This can be a database issue as well. Like you connect to a database is busy, it ran out of connections, and your code is going to stuck there. So when such a situation comes, this will be helpful to pinpoint this is where the error happened. Okay. Yeah. Okay. So what we have seen, right? All these challenges is basically we were able to overcome using distributed tracing, right? How we were able to do that is because our application, right? If you look at our each of our microservices in the system, each of them is producing some output. Basically, whenever something happens within the system, it's telling that, okay, this happened. Like request comes in, it is saying that, hey, I received a request. Then it says that, okay, now I'm going to call the next service. Then it is saying that, hey, I'm going to call the database. I called the database and got a response like this. Like that, whatever happens, it's going to send it as an output or a signal. So we took that output, put it in some presentable form, that is our the tracing UI, and then we looked at that output and figured out what happened, right? This is called observability. Basically, you get a comprehensive understanding of the system by looking at its output. That output is called telemetry data. So it can be trace, it can be metric, it can be log. Just that it need to produce that output to know that what is happening inside. So if you take this is similar to monitoring, right? Like monitoring is also kind of similar, but there is some difference. So if you look at this picture, it's a car dashboard. Okay. So in the right side, uh, we see that the dashboard is showing a warning. It is a engine overheat issue. So someone has decided that if engine overheats, it's an issue. So we need to indicate it to the user. So they have predefined it. Like this is a problem, we need to show it to the user. This is monitoring. Sometimes it can be extended to alerts also. But observability is much more than that. Observability is car, right? It is going to emit a lot of signals telling that, hey, this happened, everything, whatever you do, you press a button, it's going to emit a signal. And we collect all of that things and then use that for diagnosis. This is observability. So it's like a super observability is a super set of monitoring. Okay. Yeah. Now, monitoring, right? It's going to tell something is wrong. Observability, it's more than that. It's going to tell why something is wrong and where something is wrong. So to make our application observable, right? We need to, like I said, the application need to emit telemetry data. So how do we emit telemetry data? So we need to write some code inside, write some additional code inside our application, which will collect some information and send it to some system periodically, right? So that is where open telemetry comes into the picture. So it is for instrumenting your code. Okay. So it provides a framework and toolkit for facilitating the collection and exporting of your generation and exporting of your telemetry data. The facilitation is very, very important here because open telemetry itself, right, is not a observability or a tracing or a storage or any system. It's not at all used for storing the traces and then analyzing the data or anything. There is a common misconception with people that open telemetry is a tool, like a product which you can put in your environment, and it can provide you visualization about your system, and you can query the data and understand issues. But that's not true. It helps in facilitation. That facilitation is very important. Now, whatever after the facilitation, whatever data you got, it's going to be sent to any system, any observability backend or front end, meaning a storage where you put the trace metrics, everything, and then you have a front end where you visualize whatever is stored. So that is given to other tools. You can put any tool there, like you can have open source observability backends, you can have paid commercial backends, whatever it is, you can put it. Now, is open telemetry the only way to instrument your code? No. It's a standard. It's a standard. It's one of the ways. Traditionally, if you have seen, this have been done by many vendors in the past as well. So you get a subscription from them, you get their SDK, put it in your code, emit some data in the format they accept. They'll store it, and they are going to provide you some visualization or some dashboard, some creative ways to show it to you, right? So this has been there for long. But open telemetry, what they have done is they have standardized it and made a standard format to send the data which everyone can use. So that's why it has become a de facto standard now. Like observability means people are directly going for open telemetry. Previously, it's only traces. Nowadays, for logs and metrics also, it is a very, very standard thing being used by many people. And it's widely adopted also because it's integration with many different tools. You don't have to worry about, okay, for collection, I need to use one vendor. Then for traces, I need to use one vendor. For metrics, I want to use another vendor. You don't have to worry, and your code need to be instrumented for both of that. It's not there. You just use one tool. You produce the output in one way that each vendor, just that all these vendors that you are using need to accept that, talk in that way. That's it. So how it is able to provide that integration is the most important thing is its protocol, the OTLP protocol. So all we have to make sure is our code is generating telemetry data, traces, metrics, signals, all those things in this OTLP format. It is the data model and API contract in which it tells that this is how the telemetry data should be. If we can do that, and if the vendor supports that format, we are good. So that is one of the important point in open telemetry. And nowadays, many vendors are supporting this. Second important thing is SDKs. So open telemetry is a CNCF project. It's a very big project. I think it's a top project in CNCF. They provide a lot of SDKs for more than 15 languages. C Sharp, .NET, even Rust is there, Golang is there. So this SDKs, right, it helps to generate the telemetry data. So we know that we need to generate it in OTLP format, but in code, every time people cannot sit and write some code to generate it in OTLP protocol format, right? So it provides SDKs. So we just include the SDK. We write some wherever we want, like we saw in the tracing UI, right? for when the request comes in, I want to collect some data. So you write some code from by extending whatever code is available in the SDK, it's going to send the data. So the SDK is very powerful. One side point here is there are some situations where you will not have flexibility to change the code, right? You cannot go to some code. Maybe you are some pure ops person. You are hired to just increase the observability of some system without touching their code. So in that situations, there is something called auto instrumentation as well. So we just need to run another process alongside the application with some privileged mode. It's going to look at the kernel level system calls and provide telemetry data. But this one, if you see, it is not very flexible. It won't be targeted. You will have a lot of noise as well. To start with, to improve the observability, to start with, auto instrumentation might be good, but it's better to go for manual instrumentation as well. Yeah, we spoke about a lot of telemetry data, right? Telemetry data everywhere. So that telemetry data is called signals in observability. That is a proper terminology. And in open telemetry, sorry, open telemetry supports many signals. Okay, one is logs, which is a very logs is a legacy signal. It's been around in our industry for ages, right? Everything has logs. So everyone knows what is logs. It's a time-stamped record. And we have metrics. Metrics is just a measurement, and it will have a timestamp as well. And it has traces. So traces is what we saw. So it shows the path taken by the request within your system. So traces is what we are going to cover in detail. Okay. Yes. Yes.
On the SDK, you said auto implementation, right?
Mhm.
So is it like whatever the logs that is already generated by a traditional system will go to a middleware that converts it into an open telemetry?
So it depends on the language we are using. In Golang, how it works is you have your application, then you have another one process which OpenTelemetry will give. We'll run it alongside this process. Basically, both will run together in a single mission, and this additional process which does the auto instrumentation is going to have higher privileges, maybe root access. Then it is going to inspect. There is a concept called eBPF, using which you can put your code into there is this BPF, you can put your execute system calls via that interface. So they inspect all the things at the kernel level and understand what is happening, what is being done by the application process. So in Golang, it's implemented that way. But maybe in other languages, I don't know how they have implemented.
So in Golang, whatever you are saying is like when a console log is happening, you have to override the existing with the new log. Is that?
No, it's not about logs. It's much more than that. For example, your Golang application is making a HTTP call.
Okay.
So for HTTP call, what the code will do? It's going to make a system call telling that, hey, I want to send a network packet. So this is the data of the network packet, and going to do something at the low level, right? They are going to that low level and finding out what is happening, and then exporting it as a metric or a trace or a signal like that.
Got it. So basically, goes in deep about whatever that is happening, and then it collects the
Yes.
metrics or
Yes.
traces out of.
Yes. That's why it's running in privileged mode, because a normal process cannot go and inspect all the system calls of another process, right?
Can you give me some example of this? Like how what are the increment solutions that is available?
Increment?
So you said that auto increment, right?
Auto instrumentation.
Sorry. Any example, like let's say if you say for tracing, use the Jacker, or we can use any other solution. Right? Likewise, if the for the auto instrument, is it that itself is a solution, or is it like that is a common practice you can use implement using some solution like a
Yeah. We have multiple options. One of the options is open telemetry itself is providing that uh, that we'll call it a sidecar or something. That is that open telemetry itself is providing. There are other solutions as well. There are some service meshes which work at kernel level and collect the data. Right? We don't need to put all these things into your code. Your service mesh itself will look at the network and find out, okay, this is what is happening in the network, and it will send the signals. but it is all in a very starting stage as far as I know. Yeah. Okay.
So the instrumentation that you talked about, that's how, yeah, it was able to find the customer ID and able to give the trace.
Yeah, the what I talked about is auto instrumentation,
Yeah.
but in this particular code that I showed, we have done instrumentation using SDK only. So we are only, let's say you have logged in, most probably you will have some token associated with you, right? With that token, we are identifying the customer ID. So we know that this is the currently logged in user. We take the ID and put it into the context, which will be passed across. So this is all manual instrumentation. We are not using any auto instrumentation.
And this is similar to how Datadog works.
I have not worked with Datadog, but yeah.
Yeah, we also build context on top of
Yeah.
every log.
Mhm.
Every
It is similar to correlation. Basically, my request is this. I put some ID to the request and send it across everywhere. So I know that this is part of same request. Yes, similar to that, but just an extension to that. They have built more on top of it and put some standard to it. Like you follow this way, like that. So because everyone was putting some, they were putting correlation ID, request ID, every tool was doing some different ways. They have come up with one standard. Yeah. So we'll deep dive into distributed tracing. Yeah, already we know that what is distributed tracing. So in OpenTelemetry, as per their standard, how this tracing works is it's because of two main things. One is span and another one is context propagation. Okay. We'll look at what is span. This image is not clear actually, but we have seen this in the Agar UI before. So span is a unit of work or operation, meaning you can define it. What is your unit of work? It is up to you to logically define what is a unit of work. So in our case, a request came inside our application server, that is our fiber application server. It came in and it's going to be handled by some function. That is a unit of work. Then it is sending a HTTP request to another system. That can be another unit of work. It reaches recommendation service and I'm going to do one extensive operation. Like it's going to run a very big logic, consuming more memory, consuming more resources. It's going to do some expensive operation. That can be one unit of work. So we define what is unit of work and we create the spans. So in our case, there were like around 15 spans. I think there were 15 spans that we have created. Yeah. So what span contains? So span, let me go to that. Okay, or it's fine. I'll show it here. So each span contains span ID to uniquely identify the span. Then all these spans will have a trace ID. So it is for correlation. So we have 10 unit of work happened, but how do we know it's all part of same request? So that's where this trace ID comes, which is nothing but correlation ID. They have just given a good name and standardize it. Then we have pair and span ID. This is for building the relationship. Like you have bunch of spans. How are all they related? Like span 1 was created first, span 2 was created next. So to build that relationship, they have pair and span ID. It's called causal relationship. Then start time, end time, we saw already when looking at the performance issue, right? Every operation will have a start time, end time so that we know how much duration it took and identify which operation has taken a long time. Then logs. So logs are contextual. It is possible that in every unit of operation, we can put that operation's log alone. So we know that in this operation, this is what happened. And attributes are some arbitrary key value pairs. We can annotate our spans with some attributes. For example, we saw HTTP status code, we saw customer ID. These are all attributes that we can add to the span. We just annotate it so that we can identify it in a better way. Yeah. Trace, we all know. We have seen span. So collection of span is trace. So context propagation. So we see that spans are getting created in across services, right? Like request came to front end service, it created a span 1. Then request came to front end service called customer service. another span got created. So both are getting created in two different services. It could be like they are running in different missions also. How span 2 knows that it belongs to trace 1? How span 2 knows that its parent span is span 1? Somehow we need to pass around some information, right? So that is called context propagation. Basically, context is nothing but some information that will be sent to your sending service and the receiving service. Propagation is about passing that context object around. Okay. Yeah. Again, same, it's for correlating and building the relationship between spans. So how they are passed is, for that also they have defined a standard. So W3C has this standard for trace, a standard called trace context specification, where they have defined some headers that we can use for passing correlation related information. So in OpenTelemetry, there are many propagators. The default propagator is this, based on this W3C trace context, which uses HTTP headers. But there are other ways to pass data as well. If we want, we can extend it, or we can use some other ways as well. But the default, when we use the OpenTelemetry, it's going to be, the context is going to be passed using headers. So here we see that there is this is not visible. Actually, it's called trace parent. The header is called trace parent, and another header is there called trace state. So trace state is a optional header. It is used for passing some arbitrary key value pairs. For if you're using any vendor and they need some additional information, we can pass using trace state. The important header is trace parent. So if you see trace parent, right, it has trace ID and span ID. Apart from that, it has 00 and 01 at the end, but it has the trace ID and the span ID. When the HTTP call goes from front end to customer service, it's going to put this trace parent into the header, and it will put it transparently. We don't have to explicitly pass all these things. The SDK will take care of all these things. So once it is passed, it's going to associate every span that is going to get created inside customer service. It's going to associate to the trace and span accordingly. This is called context propagation. It's like a magic that happens in OpenTelemetry. It's not a magic. Basically, it's just passing around data. Yeah. There is one another thing called baggage. Basically, it is similar to context, but for passing any arbitrary key value pairs. Let's say we saw about customer ID, right? I was able to query the traces by passing a customer ID. So this kind of additional information can be passed using baggage. For example, let's say a request comes to front end service and you want to capture the origin IPs. So origin IP, usually if you want the exact correct origin IP, you have to capture it at the first request, right? Once it reaches front end and the request goes to customer service, if you try to get the origin IP, it's going to be wrong. So this information is available in the starting of the request. So these kind of information, we can put it inside baggage and then pass it across. And next service or whatever is further down, they can take it from the baggage and make it part of any signal. In whatever way they want, they can use it. Right? That is baggage. Yeah. One important thing about baggage, generally people in the OpenTelemetry community, people hate baggage because it is like open, it's very flexible and it allows anyone to pass anything, right? So the security consideration need to be taken care of, because if you see customer ID, someone can easily pass a customer personally identifiable information into that, like a Aadhaar number or a credit card, someone can put it. And where the problem comes is, it's not like all our requests are going to be inside the system, right? It is possible that we will be using some third-party APIs to send some analytics or something. So that time, our HTTP request might include this data in the baggage, which will be passed as a header. So it is possible that you end up sending this data to the third-party system unintentionally. So need to be carefully used. Okay. Yeah. So far, any questions?
Especially on
Yeah.
backend.
Mhm.
So it's when we are communicating with from our system, we are communicating with the third party. We need to be mindful about what are the headers we are going to pass by not
Or
passing this.
we can use a different HTTP client. So you have a HTTP client which is capable of emitting telemetry data. You can have another HTTP client for the third-party API calls, and it will not have, this tracing or.
So this is on a HTTP level rather than a log level.
Yeah, it is on the so we are mostly looking at tracing. So it can be any communication, right? So if you're connecting to database from through internet, it's maybe a TCP call, so it can also have data. So it's at that client level, whichever client we are using, we need to ensure that we don't put all these things into the baggage. Yeah. So there is before going into the code and showing how this tracing and everything is implemented, we'll just see another component that is available in OpenTelemetry, okay, which is called OpenTelemetry collector. So if our application is capable of emitting telemetry data in OTLP protocol format, we can integrate with any system, right? This OpenTelemetry collector, if you see, it is sitting in between our application and the observability backend, which we'll think like it's really, is it really required? So our application is generating OTLP data. Vendor is capable of receiving OTLP data. Why do we need a collector in between? That is the obvious question usually comes, right? So that is where we'll understand why it is required. It is much more than just receiving the data and sending. It is much more than that. So this collector, right? We can do some. We can offload certain work to the collector. For example, you have 10 services, and your observability backend is failing for some reason, and you want to retry, like you want to retry sending the telemetry signal. So in every application, we cannot go and implement retry. So collector can do that automatically. And batching. So you don't want to make too many requests to the observability backend. So what do? We batch and make limited requests. All these common things can be put inside the collector. So if you see the collector here, right, it's not just an input output. In between, you see something called processor. So we can implement our own processor. We can, if you see, there is a batch processor. So it has a receiver. It has a receiver is sort of an input, exporter is an output, and in between there is processor. So we can do some transformations. For example, we get lot of span data, and we want to count the number of spans coming from certain endpoint, and we want to expose that as metric. So that we can do in the processor. Similar to that, we want to filter data, like some sensitive information we are putting in the span, and we want to use some regex and then do the filtration and drop it before sending it to the observability backend. We can do that. And let's say we are using two observability backends. One is internal open source, another one is third party outside, and we want to send everything as it is to the internal one, but we want to drop some data and send to the external one. These things also are possible. So that's why the collector is, we should have collector actually. You should not skip it basically. Okay. Yeah. And another advantage is the centralized configuration, right? If your application, let's say you have like two different vendors for tracing, monitoring, all these things, you don't have to put the collector configuration everywhere in the application. If it is one collector, your application just need to send it to the collector. That takes care of integrating with different vendors. Like let's say you want to try out these days, right? In the observability space, there are a lot of new people coming, and they are also applying AI on top of, because you are giving a lot of data. Tracing every request is sending a lot of data. So a lot of observability vendors are applying AI as well. So there are new vendors popping up, and new features are being added. So you want to definitely whoever is working on this thing, definitely they'll try out many things, right? So if you're doing any POC, you don't have to touch the application. Just in the collector, you have to just provide one more output. It will just work. And API keys. So if you're having any API keys to, let's say, connect to a third-party vendor, you can manage it in one place. Let's say the API key is compromised. You don't have to go to each microservice and then change the configuration. So the collector can take care of it. Yeah. Another important aspect is the egress traffic, that is the traffic going out of our system, right? So if you are using any vendor that is outside your system, you will need internet, right? If you have collector, your internet access will be restricted to the collector. If you don't have collector, all your applications now need access internet to send the telemetry data. So this is another aspect. So instead of giving access to a wider range of IP addresses, you can just limit it to the instances, collector instances. Okay. Yeah, and collector can be deployed in different ways. First one is obviously no collector. We don't need a collector. So you have application, you have observability backend, application directly sending without the collector. So this is good to start with, but once your application grows or once it becomes complex, better to put a collector. So we can run it in agent mode. This is very common in Kubernetes and all. So here the collector runs near to the application, meaning let's say in Kubernetes, or let's just take plain VMs. You have n number of virtual machines and your applications are running in multiple virtual machines. So you put collector in each of the machines. So whatever telemetry data an application has to send, it will send to the nearest collector that is within that machine. So this is one way. And another thing about agent is open telemetry collector is capable. Open telemetry has, apart from traces, it has metrics as well, right? If you want to collect system metrics, let's say from the VM, you want to collect CPU, memory, disk, all this metrics, then the collector has to be in the system. We cannot keep the collector outside and expect it to collect the system metrics. So in those situations, it runs in runs as an agent mode. Okay. Another is the gateway mode. Here, collector a collector itself will be like an application that will be scaled. So you have n number of collectors, you put a load balancer in front and everyone send the data to the load balancer. This is another way. There are, in complex systems, there is a mix also. We have both agent and gateway. This is useful when let's say you have lot of processing happening in the collector and you don't want to manage those processing in every collector. You want all the collectors, basically you are segregating responsibility. All the collectors that are running near the application, the responsibility is to just get the data and send it out immediately. That is its responsibility. The gateway collector, which is separate, its responsibility is to do bigger things like transforming, filtering, all these things it will take care. And that will have connection to internet to get sent to any external observability backends. So like this, a combination is also being used.
Can you help me to understand the agent plus gateway part?
Agent plus gateway. Okay, so basically we run collector. Imagine you have many VMs. Okay, you have applications running in all the VMs. Now you install the collector as an agent in each of the VM. Then you have one another collector running in separate VM that runs as a gateway. Now all the collectors that are running as agent, the responsibility is to get the signals from the nearest applications, that is applications running in that machine, in that particular machine. Then the responsibility of the gateway collector is to receive all the signals from all these agents and then do some operations like filtering or whatever filtering or transformation, whatever it is, and then send it to the observability backend of choice. That is the splitter. So it is not really needed on day one. It is needed only when things grow. Like you feel there is lot of changes happening in your collector. Like you do a lot of transformation. You want to deploy different processors, or you have strict security consideration. You don't want to expose this thing to internet, the agent to internet. All these things are there. Then we can think about it. Otherwise, it's a complicated thing, right? You send data to one place, then that sends the data to another place, then that sends to another place. It's all complicated, right? Yeah. In this Gringotts Bank application, what we have done is the collector is deployed in agent mode. Basically, it is sitting in between the Gringotts application and it is sitting in between the Gringotts application and the Jaeger, which is our observability backend. So collector is not really needed in this small application. I have just put the collector to demonstrate. Okay. So Jaeger, right? It's a complete distributed traces platform. It is not just that UI that I showed, the distributed tracing UI that I showed. It is a one distributed tracing platform. In our case, we are getting the data from the application and then sending it to the collector, and then the collector is sending all the data signals to the Jaeger's OTLP receiver, and Jaeger is storing it in memory basically, and then powering that UI. This is for development environment. That's why it's like that. In actual production, this whole backend, right? It's going to have bunch of components. Basically, there will be two components. There will be a storage to store all the signals. Then there will be some front ends for visualizing the data. So in case of Jaeger, we can use Cassandra or Elasticsearch. There is Grafana Tempo also, which can provide a view of traces, which works with Mineo object storage. We send the traces to Mineo, and Grafana will be powered using Mineo. And there are a lot of commercial vendors in this space as well. I think Honeycomb, Dynatrace, all these people are there. And they all agree the OTLP form. They agree to the OTLP format of data. So you can use multiple vendors, play around and figure out what is useful for you. Yeah, we'll get into the code. Before that, if there's any question, then we can see. Cool. Yeah, we'll get into code. Yeah, we'll take one service, okay, and see how we have used the SDK to uh, to generate signals and export it to the OpenTelemetry collector. Okay. So OpenTelemetry collector is another dependency for our application, which is running another. I have in Docker Compose, I have OpenTelemetry collector running. If you see here, it is having 4318, which is the OTLP HTTP receiver endpoint. So our application will be sending the signals to this OTLP HTTP receiver. Okay. So I'll take the front end microservice. Yeah, this is the main.go. So this is the starting point of the microservice. So here we are initializing tracing. Yeah. So if we see, we are creating a trace HTTP. This is the SDK. So if you see here, this is all coming from the OpenTelemetry. It's all imported from OpenTelemetry. Basically, it provides almost everything for Golang. It's very stable. And our endpoint is localhost 4318. This is where we'll be sending all the telemetry signals. Okay. Then after creating client, exporter, everything, we are setting up something called a trace provider. This trace provider, once it is created, it is set up in the global context. This trace provider is what is used to create spans. So we cannot create trace actually, because trace is not an object. Collection of spans is trace. So once this trace provider is available, you can create spans. So it is set globally. And additional to that, we also have, I showed something called processes, right? Which was showing the host name and everything. So if you see, it is giving information about what is the PID of the front end service, what Go version is used to build the things, what is the host name in which the application is running. These are all attributes. So OpenTelemetry itself is providing some way to enable some attributes. So if you do with OS, it will put the OS related information into your spans. So this is configurable. If you want, you can put it, or you can choose to write your own attribute identifiers. These are called attribute identifiers. I think you can write your own attribute identifier which can discover the environment, where it is running, what is the name of the system, all these things it can discover and then put it into the span as a attribute. Okay, once we look from here. So first the request is coming in and it is going to be handled. We told that it is one unit of operation, right? So we need to create a span when the request enters. How do we do that? So let's go to the main application. So after setting up tracing, we are creating server, and we are calling the run function of the server. So inside run function, if you see, we have defined our handlers. If the request come to recommendations, then use this function, execute this function, right? Now, this we want to treat every request that is coming into our server as an operation, and we want a span for it. We want to track it. So for every handler, we cannot go and write that particular code. So we are using a middleware here. Okay, it executes for every request. Now that middleware is something we can implement. Like we can write a middleware that will take the trace provider object and then start a span before the request, once the request reaches, and after the request is completed, it can stop the span. We can write it, but actually Fiber itself is providing that middleware. So if you see Hotel Fiber, uh, it is in the Fiber contribution library. There is Hotel Fiber middleware available. So let's look at the code of the middleware and see. It is going to be the same as what I said. So inside the middleware, we are taking the trace provider from the global context, whatever is globally created, and then we are creating an object called tracer. This tracer is going to help with creating spans. So inside this middleware is going to return a handler function. Let's go to that function. So this is our actual middleware handler function that will be executed when a request comes inside. So inside, when the request comes, what we are doing here is we are taking all the request related information and we are creating a span here. So first, this is the span creation. So when the request comes inside, we are creating a span, and in that span, we are going to put all the information related to the request. Then we are telling that at the end of the handler, the middleware handler, you close the span. So that is differ. Differ is a keyword in Golang. Now, after creating the span, you need to hand it over to the next middleware or the actual handler, right? So we call the next method, which is going to execute. If there are any middlewares, it's going to execute, and then it's going to do the actual handling of the request, and it's going to return back the response. So after it is done, we get the response related data. What is the content length? What is the status code of the response? How much time it took, the end time of the whole process. All those things we capture and put it back into the span as a attribute. All those things happens here, right? And then we stop it. So this is one way to instrument. Like it is the Fiber itself is providing it, but it is possible that we can also write it. So yeah. I'll show an example where I have created a custom span. Okay, and if we look here, right, this is the request that came in for the handler. We have created a span, right? Now, similar here, the front end is making a HTTP request. So the client need to create a span. So the HTTP client need to be capable of creating span. So if we go to our front end's HTTP client, right? Here we are creating a HTTP client. So this HTTP client is a wrapper around, it returns a client. It is a wrapper around Golang's HTTP client. So this is the base HTTP client provided by Golang. What we are doing is we are just wrapping around that and then modifying its internal state. Basically, it has something called a transport. Transport is what decides how to make individual requests. So instead of using the default transport, we are just replacing it with Hotel's transport, which will help in tracing that call. Similar to that, you can use for DB, Redis, anything, right? Even if it doesn't have that feature, you can go and implement it. Okay, yeah. In the interest of time, I'll just show the custom span alone, and then we can close. Okay. Yeah, in the recommendation call, if you see here, we see something called compute offers, right? This compute offers, let's assume it's a very complex operation. We want to track it separately. We want to get many signals out of it. Okay. So in the service recommendation server, yeah, this is where we are calling the compute offers. So inside compute offers, we want to, before starting the computation, we want to create a span. Once it is completed, we want to end the span and we want to put some attributes into it or logs into it, right? So what we are doing is we are getting the trace provided from global context. Then we are creating a tracer. Then we are starting a span and we are ending the span, telling it to end the span at the end of the function, right? And whatever operation happens of after that, let's say I have put a log here, everything will go into the span as a log event. So this is how we create custom spans. Okay. Any questions on this? Like any question on how the log is going into the span? Huh. Yeah. So basically how the log is going to the span is we have set up a logger as well. So in the starting of the application, right, we are using a logger called Zap. Uh, it's a logging framework for Golang provided by Uber. It helps to create structured logs. Now, this logging framework is set up using this logger function, which I have written separately. So every time you start a logger, right? When you want to log something, you need to get the instance of the logger. When we get the instance of the logger, we are passing in the context. That context will hold all the things related to the traces and spans. Basically, in Golang, context is a way to pass around data across many things. So whenever, if we go to our recommendation server and look at this compute offers, if you see, we are creating a logger and passing in the context. This context is a context after we created the span. So this context is going to hold the information. So in our logger, the actual logger, if you see, we have wrapped it. We have wrapped the Zap logger with hotel Zap logger, right? This hotel Zap logger is capable of extracting the information from the context and add it to the span. That's how it is. Like whenever you do log.info, apart from putting it into your std out, it is going to put it into the span as well. This also can be implemented in we can even implement it on our own. Just that library is providing it. Zap is a logger. So we have extended the function of Zap. And so as a logging framework, what Zap does is when you put a log statement, it is going to put it into the std out or some file that is specified. We have extended the capability of that to put it into the std out as well as take the span from the context and add it to the span, to the current span. Like that, we have extended the functionality.
So is it like the span will have the log now, or the log will have the span ID, which is more appropriate?
Span will have the events. It's called events. So basically, we add events to the span. Log is a type of an event.
So here the logs will not go directly, but it will go through the spans.
It takes the current span. So context as a way to take the current span. Then it says add a new event. Type of the event is log, and this is the log.
Okay. So the logs will not go as a standalone thing. Instead, it will go as part of all the spans.
Spans, yes. That's why it is contextual to that span. It won't be appearing anywhere else. Only in the span it will be appearing.
No, I was assuming that the logs are going to have the span ID, and then the hotel is going to process. Okay, for this span we have got the so and so log, so this should group under this.
No. It will if we look at our actual tracing data generated, whatever data, the OTLP data that is sent to the collector, right? If we look at it, all these things will be present. Yes. Everything will be. Yeah, we are almost running out of time. So yeah, if there are any more questions, we can discuss. Uh, yeah. So the code that I have used is available here. If you want to try out any distributed tracing platform, right, you can easily try it out. Basically, you can replace Jaeger with Grafana and try it out. Like that I have written, so you can use it to play around with these frameworks. Okay, yeah, thank you.